All right, so welcome to our second talk today. So it's Junyi, and he will talk about the multiplier spectrum morphism is generally injective. So please.
Okay, thank you very much. This talk is a joint work with Zhu Chaoji. And maybe we first mention the motivation of this talk. It's from linear algebra and very basic fact. So let A be a matrix, n times n matrix. Then the spectrum of A is exactly the set of all eigenvalues of A. Here we're counting with multiplicity. Then we can view this set as an element in Cn, but we need to quotient the symmetric group. And using a symmetric polynomial, this is isomorphic to Cn, right? And okay, and this spectrum is invariant on the conjugation. So this defines a map from maybe we can think as a moduli space of a matrix. It's the space of n times n matrix, but we quotient the similarity relation, and this maps to Cn, which send any matrix to its spectrum. And this map is not injective, but generically injective. Such phenomena appear in many subjects. I think a famous example is in one paper of Carter in 1966. Can one hear the shape of a drum? Okay. So in our talk, we focus on complex dynamics. In complex dynamics, we study F is the endomorphism of P1 over a complex number, and the degree of F equal to D at least 2. Now then, for every n larger equal to 1, if we can count the number of n periodic points. The number is exactly dn plus 1. But we count with multiplicity, and for simplified notion, we just denote this dn plus 1 by nn. Okay, then we can define the nth multiplier spectrum. It's SNF, which is the derivation of Fn at all fixed all n periodic points, and then we make them together to be a set. Okay, so we can view this set as a subset, an element in C nn, but quotient by the symmetric group SNN, and via the symmetric polynomial, this is isomorphic to CNN. Okay. So basically, the nth multiplier spectrum is just the collection of the multiplier at all n periodic points. Okay, and it's clear that this set is invariant on the conjugation. So the multiplier spectrum is just the collection of all these all the multiplier, but not just a fixed one period. It's just it's the multiplier for all the periodic points. So it's the sequence of sets SNF for all n large equal to 1. So we can think this multiplier spectrum as some kind of nonlinear version of the spectrum for matrix. Okay. So moreover, in the definition of multiplier spectrum, we use all the multiplier, but we can change this multiplier to the length of them. And if we replace all the multiplier to the norm of multiplier, then we change this multiplier spectrum SF to we call it LF, the length spectrum. And this length spectrum is also invariant on the conjugation. But we see that the length spectrum has less information than the multiplier spectrum. So the main question in our talk is the following. We want to read F from the information of SF, the multiplier spectrum, or the LF, the length spectrum. Okay, for this, maybe we first recall some definition. First is about the moduli space of the degree rational map. It's exactly the set of degree rational map on P1 over C, but we need to modular the PGL2 by conjugation. And this space is an affine variety, and its dimension is 2D minus 2. Okay, so for every n at least 1, the nth multiplier map, because the nth multiplier map is invariant on the conjugation, so it defines a map on the moduli space. It defines a map Sn from MD to CNN over quotient SNN, and which is isomorphic to CNN. The map sends F to the nth multiplier spectrum of F, and all these definitions are algebraic, so we can image that this Sn is in fact an algebraic map. Okay, now we can also think the multiplier spectrum as a map on the moduli space. So because the multiplier spectrum is the collection of all Sn, so we can think it as the product of all Sn. Then it's a map from MD, but to an infinite product from n equal to 1 to infinity CNN. But we see that the right-hand side is of infinite dimensional. So maybe this causes some technical difficulty. So however, because every map here is algebraic, so we can do something to reduce it to finite dimensional. What we do is like this. So we consider the truncation tau n equal to SE times S2 to Sn. Then this define a map MD to CN1 times CN2 to CNN. Okay, so because all these maps are algebraic and the space MD and the CNI are algebraic, so by the nodalianity, we have the nodalianity, then we can take this n large enough, which means that there is a number MD depends on D large equal to 1, such that for every FG in moduli space MD, the multiplier of f and g are equal if and only if tau mdf equal to tau mdg, which means that if you have two rational functions of degree d, if the first MD order multiplier spectrum are the same, then all the multiplier spectrum are the same. And the proof is very easy because we can look at the subset in MD square, which is the set of pair Fg such that tau nf equal to tau ng. And we see that this subset is directly closed, and when n increases, this subset is decreasing. So by the non-reality, it will stable at some for n large enough. So this proves the statement we mentioned above. Okay, so now we can just this S is some, the multiplier spectrum is something like you really need to look at all the period points, but this argument shows that you only need to look at finitely many periods. Okay. We will also need some notion of exceptional maps because in complex dynamics, sometimes for the exceptional maps, we will get some counterexample. There are two types of exceptional maps. The first one is a Lattès maps. We say that F is a Lattès maps if we have the following commutative diagram. It's something like that. We note that P1 is just it's a map from Lattès map is basically a map from an elliptical curve. So it means that we have a morphism of G on an elliptical curve E, and because P1 is just the elliptical curve quotient by the plus and minus 1. So this G descends to a map on P1. And if a rational map come from this way, then we call it a Lattès map. And it is called a flexible Lattès map if we can choose this G to be multiplied by n, and n is an integer. Because elliptical curve is a group, so we have this multiplied by n map. So if a Lattès map which is not flexible lattice, then we call it a rigid Lattès map. Another type is the so-called monomial type, which means that the RF is semi-conjugate to a monomial map, which is something like a Z map to ZD. Okay, and we say map is exceptional if it is lattice or of monomial type. Okay, so for me, I think that the exceptional map are exactly the map from some group structure. You can see that an elliptical curve is itself is a group, and G is a homeomorphism of a group. And also in the monomial type, here P1 is not a group, but in P1 it contains the group C star, and the group rho is the multiplication. Then this Z map to ZD is also a group. It's also morphism of the group, and this exceptional map are exactly maps coming from groups. Okay, now we denote by FLD to be the class of the classes of flexible lattice maps in MD in the moduli space, and this space is not so large. If D is a square, then the locus of flexible lattice is of dimension 1, and if D is not a square, then this set is empty. So we denote by MD star to be MD minus this flexible lattice locus. Okay, so in famous result of McMullen is the following. He said that the morphism tau from MD star to this C1 N1 tends to CN MD. This map is just the map from every map to the first MD multiplier spectrum. And he said that this morphism is quasi-finite in the terminology in algebraic geometry. And this just means that for every element F in MD star, the set of G which has the same value of tau is the of F. This set is finite, and we note that here we can just view this tau as the multiplier, the whole multiplier spectrum. So tau F equal to tau G if and only if this SF equal to SG. So just means that F and G has the same multiplier spectrum. Okay. So so maybe we can think this theorem as this. So so it's something like we can view it as the multiplier of F almost determined F, but up to a finite subset. A remark is that here we need to use MD star, not MD. So we need to remove the flexible lattice locus because in the flexible lattice locus, the map is always multiplied by n. So in the elliptical curve, the multiplier are the same. So for every element in this family, they have the same multiplier. But we know that the moduli space of elliptical curve is of dimension 1. So so this gives you a one-dimensional family in MD. So in this whole one-dimensional family, the multipliers are the same. So this is not a quasi-finite. So we need to remove this family. Okay. And recently with Zhu Chaoji, we also showed that the same statement holds for length spectrum. So here we can replace, if we replace the multiplier spectrum by length spectrum, the theorem still holds. Okay, so in the same paper of McMullen, he asked the following question: is this map tau, the multiplier spectrum map tau, is injective on MD star? So what he means is that in McMullen's theorem, we know that the multiplier spectrum determine the F up to a finite subset, but is it determine this F not up to a finite subset? Okay, if the degree equal to 2, the answer is yes, and this is proved by Miano. And the proof is very easy because you only need to look at the first. You only need to look at the multiplier of fixed points. So this gives you a isomorphism from M2 to C2, and Milner shows that this map is an isomorphism. However, the answer of question A is no in general. As we know, there are two types of examples. The first kind of example was given by Silverman. He considered some rigid lattice map. Okay, because rigid lattice map come from some complex multiplication on some elliptical curve. But there are some elliptical curves which are different, but they have the same complex multiplication. And so if we descend this complex multiplication to map on T1, then you get two different rational map. And so this give some example that the multiplier spectrum are the same, but the maps are not the same in the moduli space. And another type of example are given by Parkovich, and the construction is very simple. You just look at FG, two rational self-map of degree at least 2. Then it's easy to check that the multiplier spectrum of F compose G and G compose F are the same. Because here F and G are of degree at least 2. In general, this F and G are not, F compose G and G compose F are not conjugate. So they are different points in moduli space. Okay, so we need to modify the question. We need to modify this question A. And this is proposed by Poonen. We call it question A prime. He asked, is tau D generically injective? Generically injective means that maybe there are some, maybe there are some counterexample, but in most of the place, this tau D is injective. So or maybe we say that we can remove some low dimensional subspace such that in the if we remove some low dimensional subspace, then this tau D become injective. Okay, so so it means that there is a Zariski open and dense subset in MD star such that the restriction of tau D on U is injective. Okay, and the answer is yes. In this theorem too, we prove with a G. We show that this tau D is generically injective for every n at least 2. However, in fact, we only prove the case that D large equal to 4. But when D equal to 2, this is already obtained by Milner. And when D equal to 3, this is proved by Goto. And we see that if we when D equal to 2 and 3, all these map are explicit, so we can compute it directly, and that's exactly the proof in the dimension 2 and dimension 3 case. However, expect the case for D equal to 3, the computation is very complicated, and Goto do this computation using a computer. Okay. Before the proof of theorem 2, I want to first propose some questions. So, in theorem 2, we basically use the whole multiplier spectrum. So it used the periodic points of every period. But maybe we may ask some more effective version. So how many periods are needed? So here we propose a conjecture. We think that for D at least 2, we only need to consider the fixed point and 2 periodic points. So we think that tau D2 is already generically injective. Here, if D at least 2, if D at least 3, one can show that this tau D1 is not generically injective. This is just by the dimension reason, and by the same reason, we guess that if D at least we guess that this tau D2 should be generically injective. Okay. Another question is question C. Here we only show that this tau is generically injective. So the non-injective locus should be some algebraic subret of the moduli space. So we want to know what is the non-injective locus. Here we our conjecture is the following. So for F and G in MD star, in this MD star, so if F and G has the same multiplier spectrum, we guess that the reason that the F and G has the same multiplier spectrum comes from exactly the reason in the examples we know. So we guess that either F and G are Lattès or F and G are equivalent. The equivalent relation is generated by the following relation. So it's H1 compose H2 equivalent to H2 compose H1. We mentioned that before us, Parkovich also asked some similar question, and also the equivalence relation is also here is also defined by Parkovich. Okay, and the last question is question D. Can we replace this multiplier spectrum to length spectrum? So in fact, we up here we think that the length spectrum only consider the norm of multipliers, so it contains less information. But our conjecture is that indeed the length spectrum and the multiplier spectrum has almost the same information. Our conjecture is like this: for F and G in the moduli space, assume that F and G are not Lattès. Then, if F and G has the same length spectrum, then either they have the same multiplier spectrum, means that SF equal to SG, or the multiplier spectrum of F and G are complex conjugate. So it means that the SF is exactly the complex conjugation of SG, and so we know that if we change the coefficient of G to its complex conjugation, so we write it as G bar, then S G bar is exactly the complex conjugation of SG. So so it means that either F or either G or G bar has the same multiplier spectrum as F. Okay, now we give some idea of the proof of theorem 2. We first assume that the degree D is at least 4, because when D equal to 2 or 3, this is already proved by direct computation.
Can I ask a quick question?
Yes.
So would your argument also work in the case 2 or 3, for example? I mean, maybe with some modifications, because you said the proofs are complicated and they use a lot of computation. So could you reprove this maybe in a simpler way?
In fact, in our proof, we need the assumption that D at least 4. You will see later. We need to use a theorem of Parkovich. And in the theorem of Parkovich, he asked this D is at least 4. So that I think that's the reason we need this assumption D at least 4.
I see.
Okay, so so we first give a definition for 2 points F and G in MD. We call them intertwined if basically means that they have a non-trivial algebraic relation. So which means that there is M larger or equal to 1, and gamma is an irreducible curve in the product space P1 times P1. So on P1 times P1, you have a diagonal action. So just F times G. And so we say that this gamma is invariant under this F times G action. Maybe we need to replace it by some iterate. So it's F times GM invariant. And we think this gamma as a dynamical as an algebraic relation between these two dynamical systems. But we think it is non-trivial if it's dominant to each of the factors. Otherwise, it's just horizontal or vertical, which is not so interesting. And we can just look at the graph. So you see that in the curve, the blue one, it is invariant under this F times G M action. So it is a non-trivial algebraic relation. And the red one is not, because it is horizontal. So if we project to the if we project to the second factor, then it's the projection is just 1 point. So it's not a non-trivial relation. So we say that the F and G are intertwined, means that we have a non-trivial algebraic relation like this. Okay, so the first key ingredient of our proof is the following result of Parkovich. He showed that for degree D at least 4, there is a Zariski non-empty Zariski open subset W in the moduli space MD star, such that for every here is we have a mistake. So this is a mistake. For every FG in this Zariski open subset W, if F and G are intertwined, then they are exactly the same point. So it means that okay, maybe in the moduli space there are some points, some different points they are intertwined, but Paquet showed that generally means that if you remove some low dimensional subspace in the rest space, every element can only intertwine to itself. They cannot intertwine to other to a different point. Okay, and in this theorem, Paquet has an assumption that D at least 4. So that's why we need a D at least 4 in our proof. Okay, so in our proof, I think the idea is to look at the PCF maps. So maybe we give a very brief recall for the PCF map. So for a rational map, F from P1 to P1, we denote by CF the set of critical points. And we say that the F is PCF if the post-critical set is finite. And the post-critical set is just the union of post-orbit of all critical points. In other words, F is PCF if and only if all the critical points are periodic. Okay, so now we denote by PCFD to be the set of PCF maps of degree D in the moduli space MD. So it's a fact that for one-dimensional dynamical system, this PCF maps are there are quite many PCF maps. So the fact is that the PCF maps are Zariski dense in MD. Okay, and now we have a lemma. The lemma is the following. So in the moduli space MD, we can construct a sequence of irreducible curves Yn, such that first the union of Yn is Zariski dense in MD, and the second that for every n in this curve Yn, it contains infinitely many PCF maps. Okay, and this lemma is not difficult to prove. Basically, you only need to use the fact that PCF maps are Zariski dense in moduli space and use Montel's theorem. Okay. I think the point is that the dimension of the moduli space is 2D minus 2. And for a rational map, you have exactly 2D minus 2 critical points. So the idea is that you have exactly 2D minus 2 critical points. So you can maybe first fix first 2D minus 3 fixed point to ask them to be, for example, periodic of some type, and has only one free critical point. So this gives a one-dimensional family in MD, and then use Montel's. It's not so hard to show that for this free critical point, it can become periodic for infinitely many parameters. Okay, so the second key ingredient is the following result of G and me. And this theorem is in fact a variant of the dynamical entry-out conjecture for curves. And this dynamical entry-out conjecture was also recently proved by Ji and me. And the statement is as follows. Let V be an algebraic curve, and let phi1, phi2 be two morphisms from V to the moduli space MD. We assume that there are infinitely many parameters T such that phi1T and phi2T are PCF at the same time. Then we show that for every parameter V T in V, but maybe we need to remove a finite subset. Then phi1T and phi2T, these are 2 points in the moduli space, and we showed that for every T, these 2 points are intertwined. But here, one can see that here we prove that for every T parameter T, this phi1T, phi2T are intertwined. But in our proof, we only need one T. We only need we only need to show exist one T in V intersect W, such that the phi1T, phi2T are intertwined. So the theorem is stronger than what we exactly need in the proof. Okay, and our proof of this theorem is very similar to the proof of our dynamical Andreault conjecture. And recently, DeMarco and Mavaraki, they told us that if we only want to get the existence part, not for every parameter, there is a simplified proof. The proof is also follow the strategy of the follow the same strategy of the proof, but because you only need to find one parameter, so you can work at some periodic or at some PCF parameter, and many steps of the proof can be simplified. Okay. Okay, now we denote by Z to be the image of this tau D, and we can pick a Zariski open subset U in Z, which is not empty, such that the following holds. First, the pre-image of U is contained in the set W. This W is defined in theorem 3, which is the theorem of Parkovich. Means that for 2 points in W, they are intertwined if and only if they are the same. And we can, after shrinking this U, we can also ask that the restriction of tau D to the pre-image of U, this map from tau D minus U to U is a finite cover. It's a finite cover of some degree S. And so if this our theorem 2 is not true, if our theorem 2 is not true, then this tau D is not generically injective. This exactly means that this number S is at least 2. So we can just look at the picture like this. Here, because the S is at least 2, and this Yn is one curve we constructed before. Because the S is at least 2, we can show that there is some shadow of this curve Yn is some this Yn prime, such that for every point in Yn, because the cover is not a 1-to-1, it's a S-to-1. So you can find another point in this yn prime. Such their image on the tau d is the same point. And by some argument in algebraic geometry, you can find another curve V, which has two maps. One is phi1 and phi2. One is mapped to yn, another is mapped to yn prime. So maybe we note that this yn and yn prime can be the same curve, but this phi1 and phi2 are two different way to parameter them. This is also possible, but no problem. So basically, the idea is that here this yn and yn prime, maybe they are two curves, but we can parameter them by just one curve V and with two different morphisms. And we can write this in one lemma. So it means that we have a curve V and two morphisms, phi1, phi2, from V to this tau d minus 1u, such that the following holds. First, there are infinitely many parameters t in V, such that the phi1t is a PCF map. And second, if we compose by tau d, this tau d phi1 and tau d phi2 are the same. And third means that for every t, this phi1t and phi2t are not the same. Okay, so the third ingredient of the proof is for the following result of Ji and me and my student Gen Rui Zhang. We show that for two points F and G in MD, if they have the same multiplier spectrum, then F is PCF if and only if G is PCF, which means that whether a map is PCF, you can view it from their multiplier spectrum. Okay, so using this theorem, because we have infinitely many parameters t in V, such that the phi1t is PCF, but we know that the phi1t and phi2t has the same multiplier spectrum. So once the phi1t is PCF, phi2t should also be PCF. So it means that there are infinitely parameters such that the phi1t and the phi2t are both PCF. Now we can use our theorem phi, the variant version of dynamical André-Oort conjecture. This implies that for all but finitely many parameters t in V, this phi1t and phi2t are intertwined, but all of them are contained in W, the open set defined in Parkhovich's theorem. So in this open set, two elements are intertwined if and only if they are the same point. So this implies that the phi1 and phi2 are the same point. But in our construction, we ask this phi1 and phi2 t are not the same. So we get contradiction. Okay. Thank you. We finish here. Thank you.
Okay, thanks a lot. Yeah, let's thank the speaker. So let's start the discussion. Comments or questions? So maybe I can ask a question. Can you go back to the last slide?
Okay.
Can you say something about the proof of this theorem that that you can recognize post-critically finite maps from the multiplier spectrum? So can you give me some idea about the proof?
I think they are, in fact, in our paper with Ji and Zhang, what we prove is we prove more, and if just for this factor, we can read either F is PCF or not. I think there are many, as I know, there are at least 3 ways to prove, and let me see. Okay, so maybe for example, in our theorem, the proof is something like this. So we just look at we look at the you look at the multiplier, the non-zero multiplier. So the non-zero multiplier is an element in C star, right? It's an element in C star, and but if F is PCF, then if F is PCF, then all the multipliers are in fact algebraic. So this is in these multipliers are defined in Q bar. Is defined in Q bar, and we have a known map from Q bar. Every algebraic map, we have a known map to map it to Q. Which means that for every algebraic point, you can multiply all its Galois conjugation. Then you get an element in Q. So now you have a multiplier spectrum, means that you have infinitely many elements in Q bar star. Then you take the known map, you get infinitely many points in Q star. But in Q star, if you look at the multiplication as an addition, then you can view this Q star as some group, and if you tensor Q, then you can view it as a linear space, Q linear space, and you have infinitely many points in this Q linear space. Then you can see that you can show that F is PCF if and only if the space spans by this infinitely many vectors is of finite dimensional. So basically it means that you can get some Q vector space from the Q vector space is some kind of spans by the multipliers, and F is PCF if and only if this space spans by multipliers is of finite dimensional.
I see. Okay, yeah, thanks a lot. So are there other comments or questions?
I have a question. When you talk about the PCF, right, you talk about all the critical points are periodic, or also include the pre-periodic?
PCF, you can, PCF, a map is PCF if and only if all the critical points are pre-periodic.